Okay, here we are in week 6, and we're going to kick off this week with a discussion, real briefly here, what an antiderivative or an indefinite integral is. And essentially, what we're doing is we're taking this process that we've worked with for quite some time now, the derivative, and we're actually looking at the inverse operation of it. So, kind of how the word you know, is descriptive anti-derivatives. Okay, we're going to be doing the opposite or the inverse operation of finding derivatives. And so, kind of what we're getting at here in this slide here, I have essentially what we're going to do is we're going to, up till this point, like I said, we had a function like f of x equals x to the fifth, and we found its derivative by using the power rule or take getting f prime of x equal to or I'm sorry, 5 times x to the fourth. Now we're going to start with this function and we're going to go in this direction. So the idea is going from here to here was finding the derivative. Now going from the derivative backwards, we're essentially finding the antiderivative. Now, if you look at what I have here down on the bottom of the slide here is that this antiderivative isn't unique. And notice how we say capital F of X is an antiderivative, which means, implies that there could be more than one function. And I think these three are pretty obvious here, right? No matter if I'm dealing with capital F of X, capital G of X, or capital H of X, notice I could take the derivative of all three of these functions and it leads me to just 2x, okay? And I could use that derivative right here to analyze each of these functions, right? If I wanted to know the slope at the point, say, the tangent line at -1, I would just substitute the -1 into this function. And notice these functions are really essentially the same parent function of x squared. It's just these, have a vertical shift to them. Okay, so the slope of the tangent at -1 would be the same at all three of these functions here, right? And that would be actually a slope of -2 in that instance. All right, so essentially what we're doing here is finding the a family of functions. So if I get into the formal notation here, it's just like looks like a little squiggly line, or maybe even the letter S. But this is how we denote a indefinite integral. Okay, this is what we're going to find it is. And the indefinite integral is essentially the family of functions, all right, whose derivative is the integrand. Okay, so if I break this down, this is the integral sign, this is the integrand. Okay, this function here. We'll talk about the d of x later on, or dx later on. But so what we have here again is this C, this capital C, is just going to be an arbitrary constant. So back here, when I looked at this particular example, in this case, capital C was 0. In this case, it was 2. In this case, it was -4. So when we write plus C here, we're just saying uh, it's just an arbitrary constant. Down here, again, this was from your textbook here, gets into a little discussion of who Leibniz was, and he was actually one of the, I guess, names associated with the development of calculus, along with Sir Isaac Newton and this Bernoulli. He had a brother that was also pretty involved too, back in the 17th and 18th centuries here. So just a little historical note here where that notation came from. But essentially, we're going to be taking these things right here. And essentially, we have to start thinking the opposite of that. Okay, how do I get a derivative of 2x? Well, instead of, remember the derivatives, we took whatever was down, or the exponent down in front for a function like this, and then subtracted 1 from the exponent. Now we're kind of going in the other direction. So we're going to add 1. And how do we get a coefficient of 2? Well, we just start with a coefficient of 1 to begin with. Okay. And we got some more examples here coming up. Okay. So that's basically what I have here. I just wanted to point out in Desmos, they do have this integral sign. We're going to be using Desmos a little bit more in this particular unit. And where you find it is in the, if you go through the keypad here and then go through functions, and then you're just going to have to scroll down here. They do have a calculus menu, and you can see here that we have the different notations. We really don't use the pi a lot, but we do use the sum periodically, and obviously the logarithmic and exponential functions. So you may have noticed this earlier, so we did address it. But if I get back to my slides here, it is unable to calculate an indefinite integral, Desmos is, okay? Now later on, we're going to be putting, I think you can see there's some fields here. We'll put these numbers in. The exclamation point indicates an error, and we'll get that when we talk about something called the definite integral later on, this particular unit. But let's focus on evaluating indefinite integrals. And so if I get back to that here, these examples, I just picked out some from previous notes here. Here's number 2. And my math lab is just going to ask you to evaluate these things, and all you have to do is just, type in the answers. So, this one's a pretty basic, straightforward one here, this number 2. We start with, it keeps popping up here. Let me try to get rid of that, pin that back in there. Okay. I don't know why it's doing that. All right. Okay. So we start with 14, the antiderivative or the indefinite integral of 14x plus 8. You don't have to use the parentheses. I purposely excluded them here as long as you understand that they are implied. All right. In other words, we're dealing with this whole expression here. So all I want to do is add 1 to the exponent. So my exponent's 1, so it now becomes 2. And then what number do I have to multiply 2 by to get 14? Well, that's pretty easy to figure out. That's 7. When I have a constant, remember, if I took the derivative of 8x, I'm going to get 8. So going in the opposite direction, I just end up with, start with 8, end up with 8x here. And then, of course, we have to write our plus c for our arbitrary constant. Okay? As far as number 4 is considered, now sometimes you got to do a little extra here to evaluate these, because now we have a product here. And so what I did was I come over here and actually simplified first the integrand, okay, which is this inner function here, by distributing the 7x squared through that quantity over here. So I end up with 7x to the 5th plus 63x squared. Now I just start that like I normally would here. I'm going to add 1 to the exponent. I get a 6, and I have to say, well, what do I have to multiply 6 by to end up with 7? Well, that's just 7 6, because when the 6 comes down here, it just cancel out. Over here, I put a 3. What do I have to multiply 3 by to get 63? Well, that's just 21. So, some of you guys will pick up on this a little quicker than others, but, again, it just boils down to, the arithmetic part of it. And then, of course, I put my plus c. Okay. Then in number 6, you start seeing things that are a little more complex. Notice we see the radical sign with the number e, but, don't get too, upset by that, because essentially all e is, remember, it's a number, just like pi. Pi is approximately 3.14. E is approximately 2.7182. Okay. So it's just a number. And so what I'm going to do is, since I have a rational expression here, I am going to go ahead and, since x to the 4th is in the denominator here, I'm going to write it out using a negative exponent. So this is the equivalent to the square root of e times x to the negative 4th. Here I just have e times the square root of x. So I'm going to express the square root of x as a rational exponent, x to the 1/2. And then now I just have to deal with fractions, okay, which aren't always, the most pleasant thing. But, and I picked this one too, because you got to be careful, right? If I add 1 to negative 4, if I add 1 to it, it's negative 3. All right. So what do I have to multiply the negative 3 by to just end up with the square root of e? Well, that's just, square root of e over negative 3, right? Because when I take that down in front and multiply, they'll cancel out, and I'll just be left with e to the, or square root of e. If I add 1 to 1/2, think of it this way. If I add 1, how many halves are in 1? That's 2 halves, right? So 2 halves plus 1/2 will give me 3 halves. You have to use your calculator to figure that out, or add fractions on using a calculator or paper and pencil. And then what do I have to multiply 3 halves by to get just E? Well, obviously 3/2 times 2/3, the reciprocal is going to give me 1, and I'd just be left with E here. And then, of course, my plus C. Okay. So there are 3 examples there. These are relatively basic. I'm going to come back in the next video because just like when we dealt with the chain rule and composition of functions, when we found derivatives, well, now we're going to use a method called substitution to deal with composition of functions when we go ahead and evaluate indefinite integrals. So we'll come back with that video here and cut this one off at this point. So again, as always, hope this helps, and we'll see you next video.